In this lecture, we'll be talking about rates of change. And so we're going to start to connect the use of our limit technology to this key idea in differential calculus, rates of change. So basic definition, suppose Q is some quantity that changes in time, and Q will be equal to f of t. So some function of time tells us how much of the quantity we have. The change in Q from time t to time t plus 1 we call the increment. And we write that as delta Q. So delta Q you want to read as the change in Q. And it's simply the quantity at time t plus delta t minus the quantity at time t. So think of this as being over the interval t to t plus delta t. F of t, that's how much of Q you have at the beginning of the interval. And f of t plus delta t is how much you have at the end of this interval. Then the average rate of change of Q per unit time is that increment, how much the quantity has changed over the time interval, divided by the length of the time interval. And you can see delta t you can obtain by taking t plus delta t minus t. And we'll see an example of this in the next slide. But just as an idea, suppose you have an example where you have a car traveling, and at time 0, say Q is the distance from a geographic landmark. So you have a car traveling at time 0, it starts out at the geographic landmark. And then at time, say 2 hours, Q is 80 miles. So suppose we have these in miles. And so this is the idea where a car starts out at a landmark at time 0 and then travels for 2 hours, and the distance Q is 80 miles. The average rate of change, which would be the average rate of change of position of the car with respect to time, if we did this calculation, so delta Q over delta T for T in, say, this 0-2 interval would be f of t is 0 and delta t is 2 hours. And then delta t is 2 minus 0. And so we would have f of 2 minus f of 0. So we'll write the rest up here. Over 2, f of 2, so that's the distance from the landmark at 2 hours, which we said was 80 miles. F of 0 was the distance from the landmark at time 0. The car started there, right? So that was 0 over 2, or 40. And if you think about the units, in the numerator we had miles, in the denominator we had hours, and so this is 40 miles per hour. So this is telling you that the average velocity of the car on this 2-hour trip was 40 miles an hour. Certainly the velocity was not a constant 40 miles an hour. You would imagine the car would have started at rest and its velocity would have increased to 40, and it would have gone above and below 40 during the drive. But on average, this is telling us the car was going 40 miles an hour. Another example is that of Galileo's law, and this is something many of you will have seen in physics class. But if we have gravity as the only acting force on an object in free fall at sea level on Earth, and we ignore air resistance, then the distance it falls in feet, y, after t seconds is given by y equals 16t squared. So you may ask a question, and think of this like, you're standing at the top of a cliff, and you drop a rock, and you let it go at time 0, and then it's falling after that as you run the clock. And so you may ask questions like, what's the average velocity during why don't we say the first 2 seconds? And so in that case, our average velocity, using the same idea here, except what we'll have now is delta y over delta t. We will have delta y over delta t is the height at 2 seconds minus the height at 0 seconds over the difference between 2 and 0 seconds. And again, we can see the units height over time. So in this case, the height at time 2 is 16 times 2 squared, and the height at time 1 is 16 times 1 squared, and in the bottom we have 2. And so here we have 16 times 4, which is 64, minus 16 over 2. 64 minus 16 is 48. And so we get 24. And this is in feet per second. Again, you see the units in the top are feet, and the units in the bottom are. If you wanted the average velocity between seconds 2 and 4, then we'd write that as, it would be very similar, except you would have the height at time 4 minus the height at time 2 over the difference in time, the delta t, or 4 minus 2. Plugging this in, we would have for the first term 16 times 4 squared minus 16 times 2 squared all over 2. We have 16 times 4 squared is 16 squared, or 256. 16 times 4, 64, over 2, which is 256 minus is 192 over 2, or 96 feet per second. And so we see that the average velocity, the average rate at which this rock is falling in the first 2 seconds is 24 feet per second, but it's falling much faster on average between seconds 2 and 4. You then might start to ask questions about something like an instantaneous velocity. So for instance, suppose you're curious about the instantaneous velocity at 2 seconds. And we're used to this kind of idea. If you drive a car, anytime you look at the speedometer, what you're getting there is a reading for your instantaneous speed. So what you might do is say, well, why don't we think about it as the average speed or average velocity over, why don't we do a small interval around 2. So maybe we do something like the interval 1.9 to 2.2, for example. And that average velocity over that interval, we just go back again to our formula, the change in position over the change in time. And in this case, we have f of 2.2 minus f of 1.9 over the difference, 2.2 minus 1.9. And if you work this out, this is going to be 65.6. And so we should believe that that's going to be pretty close to the instantaneous velocity at 2 seconds of the rock falling, because this is a pretty small interval. This is an interval of width 0.3. And the idea here is you would make this, the width of this interval, smaller and smaller. And that is our connection to our idea and use of limit that we spent so much time developing. We essentially want to take a limit as the width of this interval goes to 0. So this number and this number will be getting closer and arbitrarily close together. And the denominator, these two numbers will be getting arbitrarily closer and closer together. And that moves from this average rate of velocity idea, or average rate of change, I should say, to instantaneous rate of change. That's where we're going with this. Now we want to talk about the geometry first. And so let's think about secant lines. So that's going to be the first approach that we take here. And so imagine that we have a point say and this will be our t, and then here will be our t plus delta t. So in our framework here, this is, think of as the starting time, and this is the ending time. Now we have some quantity that we started with that was f of t, and then that quantity increased to this f of t plus delta t. So this difference here is our increment, delta q, and down here we have our change in time, delta t. Now imagine that this function f of x, or sorry, f of t, is some continuous function, and let's imagine that it looks something like this. So there's our q equals f of t. So that's the actual function that tells us at any given time how much of the quantity we have. Well, let's think about what this here is, this actual quotient. We call it a difference quotient. Well, delta q, we see here, is the distance, the vertical distance between these two values, or these 2 points. So we see to get that increment delta q in the picture, to get that numerator, we just take f of t plus delta t minus f of t. Now for the denominator, we have delta t. And the thing to notice is that this we can think of as rise over run. Which we know is slope. So this expression is actually the slope of the what we call the secant line. So if we connect these two dots, that's our secant line. And the slope of that secant line is this quotient. And note, I forgot to write the delta t in the denominator here, so you'll want to add that right here. So this difference quotient is, in fact, the slope of this secant line. So remember, this represents the average rate of change of this function, of this quantity q, during this time interval. And we're now seeing geometrically that that average rate of change is nothing more than the slope of the line that connects these 2 points. And we call that line a secant line. So, trying to put this together with our intention to get to an instantaneous rate of change, remember the idea in the previous example was to try to get something closer to an instantaneous rate of change. What we want to do is shrink this delta t interval down. And if you imagine shrinking this delta t down, that will take this point and move it along the curve, getting closer and closer to this point tf of t. And that secant line will become more and more similar to a tangent line. And that is, in fact, exactly what we're after. If we take the limit as this delta t shrinks to 0, the secant line, as this point migrates its way down to this point, the secant line will snap into the tangent line. And that's when we get an instantaneous rate of change. This expression, when we let delta t go to 0, will become that instantaneous rate of change of q with respect to t at this time t. So let's draw the picture now in terms of function of x. So we were using time there. It syncs up nicely with our examples, but most math textbooks will do this in terms of x. And so we set this up as follows. We again have our function y equals f of x. And let's think about what's happening at a point x naught. And we will change x naught by h. So now, here we have f of x naught. And then here we have f of x naught plus h. And again, this is our increment. This is our delta y. And if we stay consistent with the colors from before, down here on the x-axis, this is going to be, to get the width of this interval, just take the right endpoint and subtract the left. X naught plus h minus x naught, that length is just h, or delta x. And the secant line, again as before, is pictured like this, but now we let h approach 0. And in doing so, the secant line becomes the tangent line. Which we're drawing in blue. And the slope of the tangent line is given by, we take that same difference quotient, but now we're doing the limit as the width of this interval goes to 0. But the difference quotient is the same. It's this delta y and in this case our denominator we're writing as h. So this is the limit as h goes to 0. Our delta y is given by f of x naught plus h minus f of x naught. All over h. And it's important to recognize here that now, when we don't have this limit expression out front, we have the slope of the secant line. When we let h go to 0, this orange width here shrinks down to 0. This point at x naught plus h, f of x naught plus h, migrates along the function down to the point x naught, f of x naught, and that secant line snaps into place as the tangent line when you actually take the limit. And we've used our geometry, simple rise over run, from the secant line to acquire that slope of the tangent line. And this is a natural example. This is kind of the standard approach that you do in calculus. And remember, we had an analogy where we talked about scaffolding and construction. And you can think of setting up this secant line as like setting up the scaffolding. And then when we introduce the idea of a limit, the scaffolding comes down, we get the tangent line, and we get this nice, elegant answer. And so this is the essential idea actually behind this entire course. And you can see how the idea of limit is crucial. Because when we want to go from average rates of change, secant lines, to instantaneous rates of change, we need to use this idea, this tool of limit on that slope of the secant line. Now this has a name, and we call it the derivative. So this is that expression that we derived on the previous page, and we call this the derivative of the function f of x at the point x naught, as long as this limit exists. And this is really a slide that summarizes the main points of what we just went through. First of all, the slope of the tangent line to the graph of y equals f of x at that point x naught, that is this, what we call a derivative. And we also understand it as the instantaneous rate of change of f with respect to x at x naught. So this slide gives us the key ideas of what we just seen. And in the next lecture, we're going to get into this in more detail. But it's very important to understand where this comes from. And the key thing to recognize is that it comes from taking our natural formula for average rate of change over some interval, and then letting that interval shrink to 0. And with the limit, you make the average rate of change snap into the instantaneous rate of change. And this is the idea of derivative. This is one of the fundamental constructs in calculus. In differential calculus, it is the fundamental construct. So let's recall Galileo's law and recall we wanted the instantaneous rate of change at the second, so at 2 seconds. Well, now, instead of, if we go back, recall that we said, well, let's do the average rate of change over a small interval that contains that 2. Why don't we actually use this definition to find the instantaneous rate of change at 2 seconds? That would be our derivative, or as we often call this, f prime of 2. So we're going to take this and plug 2 in for x naught. So we want, and we should recall that we have y equals f of t, which is 16t squared. And we want what we're calling f prime of 2. And using the expression we derived in the previous page, limit as h goes to 0 of, we need f of 2 plus h minus f of 2 over h. So all we've done is plugged into that previous theorem a value of 2. Instead of x, we're using t here, but the time at which we're concerned is 2. And this is playing the role, 2 is playing the role of x naught. Well, we can actually work this out. This is the limit as h goes to 0. F of 2 plus h will be 16 times the quantity, 2 plus h squared, minus f of 2 is 16 times 2 squared, all over h. Let's FOIL this out. So when we FOIL this out, we get 4 plus 2h times 2, 4h, plus h squared. And then here we have 16 times 4, which is 64, all over h. This is the limit as h goes to 0. When we multiply this 16 through, we will get 16 times 4 is 64, plus 64h, plus 16h squared, minus 64 over h. Note that those 64's cancel. And then because of that, this simplifies where we now actually will be able to cancel an h term, 64h plus 16h squared over h. Canceling an h term gives the limit as h goes to 0 of, for this first term we get 64, and for the second term we get 16h. Now, evaluating this limit, this 16h will go to 0, and we get an answer of 64. And so we know, again, this is going to be, in this question, feet per second. This means at 2 seconds, the rock that we dropped is traveling at exactly 64 feet per second. Going back to our previous approximation, when we picked that small interval around 2 and did the average rate of change, the average velocity, during that time interval, we got 65.6. Pretty close. Pretty close to what the actual instantaneous velocity was, of exactly 64 feet per second. So you can think of this like if you had a speedometer attached to this rock at 2 seconds, and you could take a photo of the reading. If it was a perfect speedometer that actually captured the instantaneous rate of change exactly, it would read 64. Realistically, the way speedometers work is our previous calculation. They calculate an average velocity over a small interval. But imagine you had a magical one. It would tell you that the rock is falling at exactly 64 feet per second. So this is the idea, and oftentimes students of calculus lose sight pretty quickly of what this means. And it's important to recognize both of the interpretations that we're focusing on here. One, this is the slope of the secant line, slope of a secant line. When you let h go to 0, it becomes the slope of a tangent line. Think of that secant line snapping into place and being the tangent line. And also the interpretation that here you have an average rate of change. When you take the limit as h goes to 0, it becomes an instantaneous rate of change. So these are two very fundamental ideas, and hopefully these examples help to illustrate this. We will get into this in much more detail. This is the fundamental construct we will be studying in this course. So we'll do many more examples, and we'll build on this. But it's really important to understand these concepts. This is probably the most important slide of the course. And yes, we will get into more detail in the next lecture.